All right, welcome to section 4.2, the mean value theorem, but we're going to start off with Rolle's theorems first. This theorem says if f is continuous and differentiable on a closed interval from a to b, and f of a is equal to f of b, that means the y-coordinates of your endpoints of your domain, then there is at least one number c such that f prime of c is equal to 0 in the open interval. It means c can't be a or b. So these are graphs of the situations that we have. In all these graphs, you can see that A and B share the exact same y-coordinate. Then there has to be at least one horizontal tangent between A and B. There could be two. There could be an infinite number. If we had this horizontal function, all these points between A and B would be C's that we could use. Example 1. Find two x-intercepts of f of x equals x squared minus 3x plus 2, and then show that f prime of x equals 0 at some point between the two x-intercepts. So this is the Rolle's theorem. So you got to show that f of x is a polynomial function, and therefore it's continuous and differentiable. That's the first thing you have to verify. Once that's done, let's go find the x-intercepts, set the function equal to 0, solve it. We can factor that, set those binomials equal to 0, x equals 1 and 2, so therefore here's f of a and f of b, they both equal 0, so that's true. F of 1 is equal to f of 2. And now we'll go take the derivative of the function. The derivative of x squared is 2x, the derivative of minus 3x is minus 3. Show that f prime of x is equal to 0, we set that equal to 0. Add over the 3, divide by 2, we get 3 halves or 1.5. And yes, that number is between 1 and 2, so there was at least one c value between 1 and 2 that had a tangent slope of 0. All right, example B. Now let's let our function be x to the fourth minus 2x squared, and let's do the same thing, but now they give us an interval, a closed interval from -2 to 2. And again, we're looking for a horizontal tangent somewhere between -2 and 2. Well, again, it's a polynomial function, so it's continuous and differentiable. So all we have to do now is show that f of -2 and 2 are equal to each other, and then we'll go find the derivative and set it equal to 0. Well, I think you can see right now both my powers on my x's are even, so whatever I put in there is going to give me positive values, so these are going to come out to be the same whether I put in a -2 or a +2. So we get 16 minus 8 on both sides, and 8 is equal to 8, so that's true. So now we'll go find the derivative. So we have 4x cubed minus 4x. We can factor out the 4x, and that gives us 4x times the binomial x squared minus 1. We'll set this equal to 0, so 4x equals 0, x squared minus 1 equals 0. And that gives me x equals 0 from the GCF of 4x, and x squared minus 1 gives me a -1 and +1. All three numbers are between -2 and 2, so therefore these are all your c values. Now you might see the author puts c's here instead of x's. They're just jumping the gun a little early. It's 6 of one, half dozen the other. Don't worry about it. All right, determine if Rolle's theorems can be applied to f. If so, find all the values of c such that f prime of c equals 0. Okay, so it's a polynomial function, continuous and differentiable. Here's our interval from 0 to 28, so we need to test those numbers. F of 0 and f of 28. Plug those numbers in. We're going to get 0 on the left because we substituted in 0. And over here, 28 squared, but that'll be negative. And here's a 28 squared, which is positive, so they cancel each other out. So that's taken care of. Now let's go find the derivative. So we're going to have -2x plus 28, set it equal to 0. Solve this for x. Subtract over the 28 and divide by -2. X is equal to 14. And therefore, it's between 0 and 28. And therefore, that's your c. All right, let's try these examples. F of x, same directions. F of x is 4 plus the square root of x minus, wait a minute, not square root, absolute value of x. My apologies. Wait a minute. Absolute values. Those give us sharp corners. So this is going to be continuous, but it's not going to be differentiable at x equals 3, and 3 is somewhere between 1 and 5. So there's that sharp corner we're talking about. Remember, in the past, you cannot differentiate at that number because we don't know how that tangent line is going to sit at that corner. All right, so off to C. F of x is equal to x squared minus 1. Wait a minute, all over x. This is a rational function. We have vertical asymptotes at x equals 0, and 0 is between negative 1 and 1, so therefore it's not continuous. And there's my picture of my graph with that vertical asymptote at x equals 0. All right, the mean value theorem, very much same components as Rolle's theorem. It has to be continuous function, it has to be differentiable, and it has to be on a closed interval. But notice they don't say anything about f of a being equal to f of b. All they're saying is that there exists a number c such that you plug c into the derivative, it has to equal, this should look familiar, that's your slope formula. The slope of the two endpoints on your graph for a and b. So this is the y-coordinate of the second endpoint, y-coordinate of the first over second x minus first x. All right, so given that f of x is equal to 5 minus 4 over x, find all the values of c in the open interval 1 and 4. That satisfies the mean value theorem. Okay, so we do have a vertical asymptote. It's at x equals 0. However, 0 is not between 1 and 4. It's outside of that open interval, so we're okay. We are continuous and differentiable on that closed interval. F of 1 and f of 4 exist, and so does everything in between. So let's find f of prime, and then we're going to find the slope of the endpoints on our interval. So f prime, okay, well, the derivative of 5 would be 0. Minus 4 over x would be technically minus 4x to the negative 1 power. Bring the negative 1, multiply it to the minus, subtract 1 from that makes it negative 2. So that gives us 4x to the negative 2 power. Then we want to write this with a positive exponent, so we move it back into the denominator. So there's our derivative. Now it's time to find the slope. So f of 4 minus f of 1 over 4 minus 1, so the denominator is 3. F of 4, we take that up here. 4 over 4 is 1, so 5 minus 1 is 4. Put in the 1 for x. 4 over 1, that's 4. 5 minus 4 is 1. So don't think I'm just transferring the 4 and the 1 over to here. That's not what's taking place. I'm substituting in. It just happens to be the same values. So 4 minus 1 is 3 on the top. 3 over 3 is 1. So the mean value theorem says set the derivative function equal to the slope of the endpoints and solve this for x. So I multiply over the x squared to the 1. Well, 4 equals x squared means that x is going to equal plus or minus 2. And so therefore my c is positive. Wait a minute. Positive 2 works, but negative 2 is not between 1 and 4. So we'll keep the 2 for c, but we're not going to keep the negative 2. It's outside of our interval. All right, try this one on your own, so pause the video and give it a shot. Okay, welcome back. We know that our function is a polynomial function, and it's continuous and differentiable everywhere, so therefore it's going to be the same for negative 3 to 4. So we're good to go. Let's go find the derivative. So 2x minus 1, that's my f prime. The derivative of 12 is 0, that's gone. Now let's find the slope. F of 4 minus f of negative 3 all over 4 minus negative 3. So I make those substitutions. 4 squared is 16 minus 4 minus 12 is a 0. Negative 3 squared is 9 minus a negative, that makes us plus 3. That'll make this 12 minus 12, that 2 is a 0. So I get 0 over 7, or just 0. So we'll take our derivative, 2x minus 1, set that equal to 0. So again here, like I said, the author may plug the c in right away. Perfectly acceptable, just go solve for it. Add over the 1, divide by 2. There's your c value. All right, find c, that satisfies f of x for, wait a minute, we have a vertical asymptote at x equals 0. 0 is between negative 2 and 2. It's not continuous, so there's not going to be a mean value theorem. mean value theorem won't apply here. There's not going to be a C there. So there's my graph. You can see it's not continuous. And even if you did go find the slope of the endpoints, you would get 1/4. But notice all my tangent lines along this blue curve, and this blue curve would be all negative slopes. So there's no way to get a negative slope equal to 1/4, just to verify that it's not going to work. Okay, 2 stationary patrol cars equipped with radar at 5 miles apart on a highway. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. So this is a perfect mean value theorem problem. These are my 2 endpoints where the patrol cars are. I need to write these as points. So my x is going to represent time. My y will represent the distance. Okay? So the first thing we're going to have to do is we're going to have to take your time minutes and convert them to hours. All right, speed, like we said, is your absolute value of your velocity function. So we can find that by the mean value theorem. So the first point in hours, comma miles, at 0 hours, I was at 0 miles. At the second point, which was 4 minutes later, so 4 over 60, got to divide by 60 to convert that into 1/15 of an hour, they were a distance of 5 miles apart. So here's my 2 points. So let's go ahead and find the slope. So f of 1/15 will be 5. F of 0 will be 0, and we'll do 1/15 minus 0. And we're taking an absolute value of this because we want it to be a positive distance. So here's my velocity. Remember, that's your position function. That's the derivative of the position function. So f prime of c will match your v of t here. So 5 minus 0 over 1/15. Well, we don't divide by fractions. We multiply by its reciprocal, and 5 times 15 is 75. So at some point between here, he has definitely exceeded the 55 mile per hour zone by going at least 75. He's probably gone faster. Okay, think of that first graph we talked about that had the curve with that horizontal tangent. Okay, so there's going to probably be another tangent line here that matches the slope of the secant. So he has definitely exceeded the speed limit. That by law they can pull him over for speeding at 75 miles per hour. It would be worse because, again, there is going to be a tangent line that's going to be steeper, which means he had to go faster and then realized, oh, there's a cop up here. We got to slow down. Didn't slow down enough. All right, so that wraps up that section. I'll see you again in a minute with the next section.